we have launch. Thank you so much. It's a huge honor to be here. Thank you. I'm going to be talking about a couple of different algorithms, but before getting into the algorithms, I kind of want to just start with, well, why you should care about me and what we're doing to begin with and give a little bit of background. So I'm Mark Nadal. I like to climb things that are very, very tall up, but that's kind of irrelevant to the actual algorithm discussion. So what I'd like to kind of start off with is actually talking about, OK, there's this pipe dream of these different applications, these dApps that people want to build, but it's often for tomorrow. So rather than actually saying, oh, here's a bunch of stuff that you could use Gun, and then you could potentially go out there and build this, no, let's actually start with some dApps that exist today by showing, not telling. So first of all is peer-to-peer Reddit. I'm going to bounce out after he just got me set up in hopefully it's still screen recording, which I believe it is. And everybody, even on your phone, hit up this URL, notabug.io. It's going to load this website that looks an awful lot like Reddit, but it is not Reddit. It's decentralized Reddit, so I cannot vouch for anything that is here content. Reddit's bad enough. Decentralized Reddit might be worse. So I'm going to pop up over, whoops. How do I screen adjust? Over here as well. But I want to show you this is running off of Gun. I'm going to scroll down to infinity load. So as I scroll through the page, you notice that a bunch of these other upvoted content, I just keep on scrolling, and Gun is able to synchronize that data. And it's potentially synchronizing it from other browser peers, from other people who are on this website right now. So I'm going to scroll up and find a victim of choice. I don't know what this is. Actually, let's do one that has some comments on it already. Scroll. I'll use this one with 3 comments. Hopefully it's not bad. I'm going to jump over to this here, and I'm going to click on the one that also has 3 comments. Scroll down, and I'm going to do testing 1, 2, 3. It's going to do a little bit of proof of work. That's not based off of Gun. That's just what the decentralized Reddit has done. But you saw that my comment instantly showed up on the other screen. Woohoo! So that's what Gun is doing. It's coordinating decentralized data sync underneath. You might be going, oh, well, this is running off of some server that's skeptical. It might be running a bunch of centralized or federated logic behind. Where you can actually click on that known peer link at the bottom. I don't know how many of these are currently up, but these are a bunch of other hosts that are also providing the data. But again, even if you're loading it through one of these hosts, when you are on the website in the browser, it's also providing and synchronizing data. So this host looks like it's a little bit slower. But if I give it a minute, a lot slower than the main one, we should see that it pulls in the content from a completely different peer. In this case, it's a super peer, but you're also pulling the data from the browser itself. So that should be pretty exciting that decentralized Reddit exists today. So now go post something creepy or weird, or I don't know. It's hopefully the community winds up being a good community versus Reddit-like. Okay, jumping back to this. So on the first day that they launched, just a couple weeks ago, they did a 0.5 terabyte of traffic on day 1. So we're talking about not only does decentralized Reddit exist, not only do these dApps exist today, but they're also doing a lot of traffic on them. There's another one that I was going to do, DTube. It's a peer-to-peer YouTube built off of Steam IPFS for videos, and they're going to be releasing a Gun end-to-end encrypted private messaging chat, kind of like Signal or Telegram. And I had a demo all prepared for you, but it stuck on that laptop, and that laptop isn't able to do the screen recording. And I also made the mistake of doing a git pull from the DTube GitHub account, and they had a bunch of breaking code, and I wasn't fast enough to rewind stuff. So you'll just have to go to that separately. There is another demo I want to show you, but maybe I'll come back to that. Oh, yes, no, I do have it on this computer. Sorry, I switched computers right before, as soon as we arrived. So I'm going to jump back. This is a peer-to-peer social network that I'm working on, just kind of in my spare time, so nothing too fancy, but mostly a for fun project built on top of Gun. So it's got this really cool ability where I can use a regular old username and password to log in. And I'm going to explain what's actually happening later, because it is actually cryptographically secure, and there is no server that's operating off of this. So I'm going to sign up. Of course, if I switch computers, I'm sure it's about, yes, let me, for whatever reason, this laptop doesn't like file having access to local storage, which is very important for doing peer-to-peer stuff in the browser. So I'm going to go to something that have just with a local gun instance running. All right, so Mark Nadal. I'm going to create a password, log in. We'll cover what that does later. And I'm going to jump to the news feed. I actually need, do you have like a random photo I can drop in as my profile picture?
Random photo.
Good, I'll use, thank you, we'll use you as, there we go, perfect. I'm going to come over to back to settings. Awesome. Well, welcome, Gabriel. I'm going to drop this in. It'll pop up there. So I'm now impersonating Gabriel. I'm going to say, hello, world. Yay. And we have my little icon. I'm going to open up this over here, take my local instance, pop over here. I'm going to create a new account. I should do Gabriel, but again, I'll explain the cryptography a little bit later. I just want to show you what it's doing. Although, of course, now that I've scrambled to go on another machine, it looks like I'm having a bit of a demo failure. So pardon me, I'm going to have to ditch and come back in a minute. So this was working on my machine. I don't quite know what the problem is over here. Would that be too bad?
No, let's go.
OK.
Because we just plugged in the HDMI.
Sweet. So draft. And I have window snapping on this machine. All right, so I'm going to create that user. I'm going to make sure that actually I need to turn this back on. OK. Now we should be in business. Let me log out just for safety precautions. Give me 1 extra second and reset everything. Local storage, clear, kill, RF. Data. And then close that. And I should be on a clean slate now. OK. Because
people, friends of yours,
they're just random faces I found. But hopefully in the future. OK, there we go. Hopefully disaster averted. User already created. Sign in. OK. Seems slightly fishy, but I'll roll with it, and I'll apologize if it backfires on me again. OK. I'm going to drag and drop in an image. So where's my cursor? So I'm going to drop Amber's photo into here, and I should have a photo here. I'm going to drop in. Go over to here, go over to the news feed. It doesn't look like Facebook, but it is. Hello, world. And there you go. It pops up instantly. Happiness and typos. The cool thing is, unlike an immutable append-only blockchain or ledger or database, a lot of things out there, I'm going to come back to settings, and I'm going to change my photo. Okay? A very important feature that for a lot of dApps we need. Oh, that actually, here, let me drop it in again so that way you see that happening. I'm going to drop in this photo. I drop it in, my previous status messages update. So this is all end-to-end cryptographically secure. We're going to go into the math and the coding and the logic behind it in just a minute, and as well as the high overload architecture. But hopefully it just gets you excited that actually we're able to create these dreamed of dApps that might replace Facebook, might replace Reddit. And you can already do them today. Now we can switch back to that machine. All right, so jumping into Firefox, which has the presentation. So now that you have a little bit of background of what can be done today, why am I building this? So fluffy kind of intro story. Back in 2010, I was working on a collaborative web design tool. It was really awesome. It was mind-blowing. It was amazing. And it forced me to learn a whole ton of distributed system stuff. I was doing, basically operational transformation level stuff, but fully peer-to-peer. Back in 2010, using CRDTs before I found out that CRDTs were even coined. But we got a little bit of traffic from the Wall Street Journal that covered us, and our entire website fell over in the middle of the night. So I get the pager call, the cliche pager call at 3 a.m. I wake up all groggy, and I SSH into the server to figure out what's wrong, and everything is fine except for the stinking master-slave database. If the database is down, then it doesn't matter. It's the heart of the whole rest of the system. If the database is down, it doesn't matter if your application server is fine, if your front end is fine, all that stuff. If it's fine, if it's not getting the blood pumped to it by the database, then you're screwed. So I realized, hey, I actually have some experience with doing these distributed concurrency control stuff. I might as well start building my own database, because I was naive. And I thought, hey, this can't be too hard. So I took all the best features out there that I liked, everything from real-time features with Firebase and RethinkDB to graph features of Neo4j and Rango to offline first features of Couch. And I can't really call Cassandra and React decentralized. There's certainly master-mastery, which is more towards decentralized and peer-to-peer, but the fact that you still need a really large server to run them on kind of makes it favorable towards server-oriented architecture versus just running on your local device. So from an algorithm side, I pulled all these pieces together, and developers loved it, right? So we've grown to about the same size of a community that IPFS was a year ago. So a ton of people have jumped in, and they're building the other cool stuff I showed you earlier on top. But now where are we going? Well, there turns out to be this one sucky, really annoying, terrible, frustrating thing. I want my peer-to-peer apps, but WebRTC still kind of sucks. And this is a problem across the board, whether it's WebTorrent. I know for Ross, and he's done some of the best work with WebRTC, whether it's the DAT team, the IPFS team, a bunch of these different teams out there. WebRTC is still kicking us in the butt. It's just super annoying. And as a result, if people like DTube, Adrian who runs DTube, he's going to be out here at the end of the month, and the guy who's running Decentralized Reddit, I don't actually quite know his name. He goes by Goldfish online, so he's truly anonymous. These people actually have real apps that are already deployed with a bunch of users hitting their site. And when IPFS and Gun and these other systems can't make these WebRTC connections, that ultimately means that all of that data and bandwidth and traffic has to get funneled through a server, which is annoying. This isn't really our fault. It's the limitation of the browser, but it then creates some issues. You might have a tendency to go the route that Facebook did. If you're providing a bunch of photos and tweets and connectivity for your users, you're going to then start mining their data and selling it to advertisers. Because if you're running this peer-to-peer app, you're trying to do it to save money partly and also decentralize the world by using the decentralized tech. And now you're paying for all of your free users. So the way we kind of get around that is we're introducing this new thing called AX, which you can think of as being a decentralized end-to-end encrypted Heroku. So we're not trying to push Ethereum aside. We're not trying to push IPFS or Filecoin aside. It's specifically around this idea of how to do data sync. If we just have a bunch of random servers out there that are all running the same system on it, then we can transmit data through, we can route data through a whole ton of different servers. Now, that winds up producing another problem, which is, aside from the economic incentive of why would you do that if you're not getting paid for it. The second problem is the only reason that I trust when I pick up my phone and dial my mom, and don't worry, I'll get to code and some math pretty soon, just to kind of frame the problem first. The only reason why I trust that when I dial my mom's phone number that my mom's actually going to pick up is because I trust that some middleman of AT&T, T-Mobile, et cetera, is going to route the call for me. The only reason when I send a Facebook message to one of you that I trust it's actually going to arrive at your side is because I trust that Facebook as a middleman is going to deliver it correctly. If we remove those middlemen and we have a fully peer-to-peer network and I wind up trying to send some data, there's no guarantee that the data is actually going to be received. So we had to come up with, well, how do we make sure that there's a cryptographic guarantee and a decentralized network of the data as actually being synced to the other peer. Thus, proof of propagation.
You don't need a cryptocurrency.
Correct. Yes. So the cryptocurrency
Why
is.
AX?
AX has more to do with economic incentive, because if I'm providing a server that emulates peer-to-peer traffic, but I'm not able to mine that data because it's all intent encrypted, then I'm basically just shooting myself in the foot with a large server bill. Now, ideally, further out in the future, when RTC stuff is working, then we don't have to worry about that. But for now, the people who are running the servers in the first place need a very strong incentive to actually run these servers and mine the AX tokens, the bandwidth off of it. So does that make sense? It's more of a temporary economic fix than necessarily the end goal. And that is because largely the tech for doing peer-to-peer stuff is still a ways out.
Even a federated model where people could essentially rent out their server time, be just as effective instead of trying to make it a cryptocurrency economic model.
Yes, and I actually answer that a little bit later in the talk, where AX actually is a federated architecture on top to make the system scalable, but it doesn't violate any of the peer-to-peer primitives underneath.
It's open source.
Yes, already is.
So SAP could fork it
Yeah,
and make a federated service.
correct. Just in terms of enterprise and blockchain note, there is no enterprise that should actually run a blockchain, because the performance of a blockchain in an enterprise setting is going to be miserably disgusting compared to permissioned peers, machines, nodes, and databases on their own server. Because with a blockchain, you have all the cryptographic overhead that you have to do in the public network because you have trust.
You can go faster.
I would love to hear more. Oh, with Rust, the Rust implementation. You could go faster, but then any Rust implementation of that system in the enterprise world without the cryptographic overheads would still outperform that system. So just be an inevitable arms race of technology. So we're actually pretty skeptical against a lot of cryptocurrencies, blockchains, and stuff out there because they're just misapplied. A quick, this is the investor pitch you didn't want me to do, but you brought it up, is I only see 3 layers as being important for having a cryptocurrency behind. And that is the physical resources that machines use. The physical resources that a machine use is storage, thus Filecoin's, and IPFS's huge explosion. Computation, aka Ethereum, Dfinity, and other ones out there. And we're missing a really important component, which is bandwidth. Marty was the very first contributor to Bitcoin after Satoshi. Satoshi even handed over the URL, the domain, and the Bitcoin client. Marty got Bitcoin onto Git and a bunch of other things. He also updated the website. Very influential in 2010. And he wound up leaving before even Gavin and others came on board. Marty has joined our team, and he's kind of got the similar kind of skepticism as I do about a lot of these blockchain and cryptocurrencies. But an important problem is that even with Bitcoin, his beloved child, right, a lot of the mining peers have our IP addresses hard-coded into the client. That is a perfect blacklist for China. To just take those IP addresses and blacklist it on their network. So that presents actually a pretty threatening, dangerous problem to the peer-to-peer world, the decentralized movement, the crypto movement, because if we still have this old model of IP addresses or domains that people are able to kind of whitelist and blacklist, we can easily get oppressed and pushed underground. And a second layer is net neutrality is pretty popular right now. And my philosophy is, why not just do net neutrality at the cryptographic layer, right? Does that, was that all right? OK, so does that make sense? So there's 3 things that we view as being important, and bandwidth has kind of been a missing equation. And if we don't solve that, it's actually going to stall progress. We're not going to be able to move forward. So how it works, again, we'll get to math in just a second. High-level thing, it actually turns out it's pretty easy to do cryptographic verification. The data is transmitted, and you would do this regardless of whether you have cryptocurrency running or not. So the laptop winds up being like, hey, I want to get a bunch of server peers that might be relaying the data. So it makes step 1 request up to, it could be a physical router, but realistically right now it's going to be a traditional server, and then in the future it's able to run on a router. And these relay peers, these propagating peers, send back in step 2 a smart contract of the rates of the bandwidth that they're going to be provided, how much the laptop is going to have to pay for bandwidth to go through those super peers. Now, This laptop in step 3 is able to choose one or many servers based off of the best rates and sends a test message, probably like 10 bytes or something like that, up to the relay peer. The relay peer is then going to propagate it out, and there's 2 important pieces right here. The relay peer doesn't trust the laptop, so it might want to check to see if the coins that the laptop is offering as a payment for the bandwidth isn't actually double spent. The laptop itself doesn't necessarily have a guarantee yet that the server is going to relay, and it turns out that it's actually faster for the server because 10 bytes at today's bandwidth rates is a millionth of a penny. It's actually faster for the server to perform the double spending check while the network is performing the check. And so I'll get back to that in just a second. Then the phone, who's the intended recipient, receives this and cryptographically signs off that they've received the 10 bytes and it acknowledges it, and that acknowledgement gets sent back to the laptop. So now the laptop, quite simply, I mean, there's nothing super complicated to proof of propagation. It's just a cryptographic signature that goes back to the laptop that, yes, they did indeed communicate with that phone. And that proof, the POP, is important for the laptop to make sure that they know the server's not screwing them over. But it's also important for the server, because now if the server has a cryptographic receipt that they actually delivered on the goods. If it winds up happening that the laptop attempts to screw over the server or run away, the laptop can hold on to that cryptographic receipt and be like, no, I did indeed send this data. And we'll get to that in a minute. I want to explain some other components of the math and a little bit of, not code first, but I'll get to code afterwards. And then once that initial session has been established, you kind of resume the flow where in step 7, we basically update our bid to the server, and we ask for more bandwidth. And then we go back through step number 4, and it flows through the system. There's a better slide in just a second, but I want to go over the math first. So there's lots of missing pieces. But you need to observe something, which is if we're talking about trying to have cryptographically verified peer-to-peer bandwidth, global traffic is about 100 terabytes of data per second. So compare this to Bitcoin, right, which is less than 200 gigabytes over a decade. So the scale that this thing has to operate if we want to hit our end goal is orders of magnitude larger than any blockchain can even possibly imagine. It's just so far beyond most of these implementations. So I'm going to be here to say, hey, sorry guys, POW, DPoS, POS, all these different blockchain implementations, they're great for certain use cases, but they are not going to let us achieve the future that we want. So math, not too bad here, a little bit fun, right? We have a private key, we have a public key, which is derived from the private key. We have encryption for asymmetric and decryption. Quite simply, a signature winds up being the decryption of the checksum of the data by the private key. That actually, when I first saw it in math, kind of blew my mind because I'm used to taking the public key, encrypting data, sending it to the private key that decrypts it, so that way you can only wind up having the private key decrypt it. But actually, the way that the signature itself happens is the private key encrypts data that then any public key is able to decrypt. I was like, whoa, that actually makes sense from an asymmetric mathematical perspective. And when I put it into math, so I thought that was it made me realize, wow, this actually makes sense underneath from a cryptography standpoint. And then same thing if you use the public key to decrypt the signature and you get the checksum of the data. I tried to make this work with Bitcoin initially because I have huge skepticism against cryptocurrency and blockchains. It's like, well, why not just use Bitcoin, right? Like this obvious solution. However, right, if we're doing 100 terabytes of data throughput per second, it's just not going to work. And there's
use a payment channel.
So actually what we're proposing here is somewhat like a payment channel. CRDT, I'm kind of Lightning channel, state channels and Lightning networks, I feel like steal a lot of work from CRDT world and cross-apply them back to the block. There's some trade-off, but yeah, it's going to be somewhat related in how it works, except for better. But so the beautiful thing with this is once we have this signature representation of the contract that's been sent for, so the bid is the data of the tokens for data. Imagine it's Bitcoin, so that way it's easier. You have the checksum of the bid, which gives you the hash, and that's signed with, it's encrypted with the private key to give you the signature. We're then able to use this to form a Merkle tree, which has some really wonderful properties if you guys aren't already aware of Merkle trees, but also some hidden hints by Satoshi in the white paper, the original Bitcoin white paper, is that we're then able to take all these bids, because I told you that the laptop and the server are going through a constant exchange of changing the contract. And that means we need fundamentally underneath Gun to act as a data synchronization protocol to make sure that byte for byte, those contracts are the same as it being mutated with a different, how many tokens are inside of it. And as long as Gun is doing its job, so you actually can't build the system without some sort of Gun-like system, we're able to then take the many different bids over time for the session of the data transmission and form a Merkle tree where we have basically the signature of the bid and its signature all the way out to the nth number of the bid in the session and the nth signature of that thing. We then take that whole thing and we can take the hash of that, the checksum of that, and encrypt it with a private key, and that gives us a super short, nice cryptographic guarantee that both parties were involved in this transaction. And the reason why that's important is because now either party can dump that to a blockchain in a traditional blockchain sense, and any other peers in the world can verify that both parties were involved. So if the laptop doesn't dump this to a blockchain, the server, it's fine. The server has proof of it. If the server doesn't dump it to a blockchain, the laptop can and have proof of it. This last two lines, this one's actually very important. It's why Bitcoin and Accident go well together, other than scaling issues. How does mining work in the system? And I'll show this in code. The signature chain on these coins that get handed off and handed off and handed off is going to grow very rapidly. And signatures public keys aren't particularly short. So if I have a token that pays for 100 kilobytes of data, and the signature chain, every single time I transact for that type of data, I have to put more data on that token that is then also getting sent over the network. Very quickly, I might have a token that has 10 kilobytes of data that only pays for 100 kilobytes. And then as I transact that a little bit more, that signature chain is going to grow and grow and grow. We might have a token that has 50 kilobytes of signature chain data on it for only now 100 kilobytes of data transfer. That means we're losing the bang for our buck over time. So what the server can do, technically any peer can do this, but you just have to be the owner of the coin at that point in time. And it makes sense for the propagating peers to do this because while their I/O is heavy, they're not necessarily CPU intensive, so they might as well perform the Merkle hash of that signature chain to produce a significantly smaller new token that can then later be circulated and through other mechanisms validated and acts as a new token. And that new token is significantly shorter, so the system is able to keep up with scaling. You don't have this all this cryptographic waste that's just generated with hundreds of gigabytes and hundreds of gigabytes of stuff that's just left over. Does that make sense?
Just to make sure that propagators check if the zone is a critical.
Yeah, that's true. If you are Merkle hashing on a double spent coin, doesn't matter how much work you do, you're getting screwed over. So this technically doesn't actually solve the double spending problem. Bitcoin is famous from an academic side for actually solving the double spending problem. Because we have network connectivity, it's actually useful that we're able to solve at least 97% or more of double spending situations because the network is live. In database world, there's a thing called a CAP theorem, trade-off between strong consistency, high availability, partition tolerance. Because POP is only checking for whether the data has been transmitted while two peers are online. If you're not online, you have to do store and forward or some other technique like using Filecoin to temporarily store the data, and then later when peers come back online, blah, blah, blah. Skip that. Point being is, if you're both online, you're not going to have partition intolerant. Like you are online, and so you're able to pretty quickly, in most cases, because Gun is able to synchronize this data so quickly using the CRDTs, which we'll get in a minute, verify and prevent double spends before they even happen. Now, that is not an academic solution. Okay, so we still actually. I'll address the academic solution in just a second. We want to give homage to Satoshi. I've not seen very many people actually use this, right? It's a tiny paper. I don't know if you guys are aware of this, but he literally suggests this. Once the latest transactions of the coin are buried enough blocks, the spent transactions can be discarded to save space. To facilitate this without breaking the block's hash, transactions are hashed with a Merkle tree. With only the root included in the block's hash, old blocks can then be compacted by stubbing off the branch of the tree. The interior hashes do not need to be stored. We don't actually need to store the majority of Bitcoin's history, but yet people are. I mean, that is great for auditing purposes, and it is very important that we have auditing purposes, but Bitcoin itself could actually be a lot more lightweight by just throwing out basically everything after, I don't know, 10, 20, whatever your threshold of blocks have committed. I hate to bring this up on a recording, but there was recently the German researchers, I believe, that found child abuse on the blockchain. And everybody was like, oh, the blockchain is an immutable ledger. And I was like, well, actually, it's the Merkle hash that's an immutable ledger. You can delete all that child abuse data from Bitcoin and still have a perfectly valid system. And so I'm not quite sure. I don't think very many people are actually using this feature. It solves a lot of things. Turns out it's great for when you're applying it to high throughput, low latency systems like bandwidth on one component. That doesn't solve the whole scaling problem. It's also important to note, and this is going to shock a ton of people and probably frustrate them, but I know better from the actual experience of working this for the last 4 years and taking a completely different route than a lot of other people in the decentralized space have, is this is happening on a per coin basis. And the reason why is if you're doing 100 terabytes of data in 1 second, okay, you're not going to have time in 1 second to sync the entire blockchain on that, okay, even with the latest blockchains that might have half-second resolution time. But if you wind up having effectively the signature chain, using Gun, you're able to make a request for just that one signature chain and sync its entire history just for that one coin and see the whole signature chain to check it's up to date. Now, again, that doesn't necessarily solve the double spending problem, but since you're online and you're syncing the information relative to this one coin, it actually gives you a really fast heads-up advantage very quickly that you're going to effectively get, let's say, the git head of a, like take a code repository. If you're able to very quickly get the git head on something, maybe it's slightly out of date, but that gives you such a heads-up advantage to be able to detect double spending in advance with a high-throughput network. But if you wind up having to sync all of the blocks and do consensus and all this extra work, it's just impossible to scale up. And I'm not saying that from a programming standpoint. No matter how much better the blockchain consensus algorithms get and the lower resolution they get, you're fighting physics here. You cannot have the same piece of information everywhere in the world simultaneously with global consensus while also having peers that are rotating on and off. So this was the slide I was mentioning earlier, and then I'm going to answer a lot of these questions I've thrown out during this process. Is just as a quick reminder, it's pretty simple. A laptop pays for bandwidth to get sent through some system. And the goal is when we actually have WebRTC working really well, that ideally you could actually run ACKs on physical Wi-Fi routers. That doesn't work right now because of chicken and egg problem. So there's immediate utility that exists today. This guy receives it, and he signs off on the first 10 kilobytes. You're again, the cleverness here is you're not doing these transactions on every 10 bytes for every photo that you're sending. Once this session has been established that's completely trustless, there is a high guarantee during this session of data transmission that the laptop is able to up the ante, where in the same way with fiat, we have a penny, a dime, a quarter, a dollar. There, in our system, may be different resolutions of coin. One that pays for 10 bytes, and there might be a single coin that pays for 10 megabytes. You're realistically never going to be paying in advance more than about 2 seconds or less. Because again, the speed at which the network can actually transmit around the world while you're online is, especially if you're running through a propagating peer, winds up being, I would have to be streaming out of my laptop like 10 4K videos in order for my buffer of how much outgoing data I'm sending to be at a layer that I'm paying 30 seconds in advance. So this isn't like your Comcast bill or something like that you're paying once a month for the entire month's worth of bandwidth. you're able to do this at very low and high resolution levels at very short time frequencies, because the only thing for this transaction that needs to happen is that this laptop, before it makes the next transaction, which happens very fast as the smart contract syncs just between these two peers directly using Gun, has to perform that transaction, which isn't too hard, before the data is even sent. So that's like, I don't know, sub-millisecond. And then the second layer is before the laptop pays again the next time for the next 2 seconds or next 1 second or the next 100 kilobytes of data, it needs to have received a pop back from the intended recipient. So if you're understanding kind of the structure, there's all these amazing cheats that you can do using these data sync algorithms, these CRDT algorithms, and using kind of intelligent intuition about the economics of the system, the limitations, the constraint of the system from ground up that you can build and make these highly scalable, performant, decentralized peer-to-peer systems that are already doing like terabytes of traffic. Now, well, what about actually solving the double spending problem? There's just a lot of cargo cult around blockchains and blockchains as a solution for everything, when actually blockchains is a very, very specific use case, which is solving the double spending problem. And that's then where I have to get all humble and honest with you guys that like, oh, okay, now I need to come back and be like, okay, we got to make sure that the 3% edge case of people who wind up double spending on the network because my wife was on the other side of the world and I spent the same coins as her, and so they're on different relay servers, if they got screwed over, well, it's actually not too bad. Even take something like Bitcoin with 10-minute blocks. We need 3 ingredients, and it's completely automatic. That Merkle, the Merkle contract that both peers have, that have a cryptographic proof that they were given that coin, and there's 2 peers that have a coin that was double spent at the same time. That technically was a cryptographic proof that they actually were supposed to get the coin, but that you try and spend it and somehow it's not. They submit this cryptographic proof, the hash of the, well, technically the full Merkle contract, to a traditional blockchain. We could build our own, but honestly, like me and Marty, we love Bitcoin and it's good enough. So it would probably still be PAL-based. There's plenty of other things we could do, but just keep it simple and straightforward. 51%, and this is going to sound scary, but you have to have all 3 components, with 2 cryptographic receipts of the same double spent coin plus 51% compute power that agrees upon that, we can forcibly remove from the fraudster the 1 missing coin. So even though that 1 missing coin might only be 1/1,000,000th of a penny in cost, that a lot of servers might just like ignore, they are academically able within 10 minutes, well, I should say 20 minutes, able to have one of these coins go to this guy or this guy, plus maybe even interest inside of those 10 minutes. Does that make sense?
How do we get to 10 minutes?
Whatever the block time is on. So like, let's say,
Which block time are you using?
like I think Definity is claiming 3 seconds. It doesn't really matter. We could build our own and just using 10 minutes as a general.
So you're offloading consensus to another consensus?
What we're doing is we're cheating. Most of the time, you don't actually need to be double spend compliant. You only need to be double spend compliant when criminal activity has happened, or when ineptitude has happened. So why not use a court system after the fact that might be 10 minutes, it might be an hour, whatever time resolution, whatever existing blockchain you want to use. I still prefer PAL in this case, not delegated proof of stake, because you can then use that to resolve all the missed double spend situations.
I can use that. Why do I need AX?
Why do you need AX? Because if you were to try and use this every 10 minutes, there's going to be
a channel solution to essentially create the speed of verifying that a propagation happened, and then I could use Bitcoin or whatever to deliver the consensus. I'm just getting the feeling that
no, I agree, and that's where I was saying payment channels might be very similar to this. Are payment channels live?
Yeah, and
Okay.
all payment
'Cause
channels
that was
require is
pretty
that we
recent.
be online at the same time.
Right.
So if I am conducting, and this is the limitation of payment channels, is that I still have to be connected to my other peer. So
Right.
payment channels, in that sense, cannot be offline; they must be online. And since we are talking about proof of propagation to another node in the system, I can run a payment challenge where we just settle up at the end.
Yes. Can you get screwed over? Because I haven't studied payment channels too in depth. Can you get screwed over?
There's a mass presentation at Bitcoin, SF DEVS, right, Rob? Can we present on mass?
On?
Partially. So, Merkleized trees are coming to Bitcoin.
Woohoo!
That's mass. That's happening directly.
Yeah, at some point.
At some point. 2 years?
They gave no time.
So a question. Remember, if we're talking about 100% of the traffic of bandwidth running through the system, that's still 100 terabytes of data per second. Is there current theoretical math, let alone implementation details, on state channels being able to do that? Because what we're trying to do is offload as much possible work, still being fully peer-to-peer, such that then potentially only less than 1% might need to run on a state channel or equivalent.
To your point, the payment channel is just for the transaction proofs.
Well, it's three-way, right? The laptop wants proof that the data was propagated. The server wants proof that that they delivered on the goods, and both parties want to make sure that if a dispute happens, that there is the exact same cryptographically signed system. So again, I haven't studied payment channels too much because I spent the last 4 years.
Payment channels is just doing swapping signatures. So as long as the signatures are being swapped as per the proof, you're done.
Okay.
And
So,
the coin, your essentially settlement really happens once you want to come on chain. So.
but won't that produce compounding problems? Because if we're talking about every 10 minutes, now you not only have the 100 terabytes of traffic that have happened that the side channel is having to do every single second, but you're across 100% of the network versus just 1% of the network. And then you're compounding that over the next 10 minutes or 20 minutes or whatever the block time is, which is going to exponentially grow for each one of these signature chains that as it's being transacted, you're going to potentially get, could be megabytes, if not gigabytes of signature chains before you even get to the next resolution. So you're not it's great that we can settle up, but if that settling up requires that we have to reverse the entire history of the last 10 minutes, 100 terabytes per second that's still not going to be scalable. Does that make sense?
I think so. Maybe I don't understand too, so go ahead.
Well, no, it's my job as a communicator to make sure that I am making you guys understand. In this model, the only thing we have to settle is the double spent things, not all transactions. And as a result, that then makes it I'd say many times exponentially more performant because now we're dealing with only the edge case versus the default case, and the default case is 100 terabytes a second. This huge savings, and for peer-to-peer systems, especially with underlying protocols and tech and WebRTC not at this layer, maybe in the future this will be possible, but this is a solution that we can build today and have working, and we know from a theoretical standpoint and also a mathematical standpoint, skips a lot of the waste while still being peer-to-peer. Sound good? Or? I see skepticism still in your eye. That's fine. Oh, wait. Whoops. So let's see if this should be fine on this computer. Let's get into a little bit of the code. This is just a sample of what might happen. So if you guys are bored by this, certainly tell me to, hey, I cannot read localhost property. I might need to switch over to, I can probably use this one.
This is still all JavaScript.
Yes. Reference implementation is in JavaScript because I believe in universal access and ubiquity. And then we can, and here's the thing. If we can get the performance working in JavaScript, a joke of a programming language, it's certainly going to be a lot more performant in Rust, C, C++. But because JavaScript is lingua franca, it winds up being it makes our bar harder to achieve. So we prove ourselves even more. And on top of that, it creates a nice reference implementation for other people. All right, so we're going to create using GUN's C system, security, encryption, authorization, 3 public-private key pairs, both ECDH and ECDSA, which is what we're using. So I can type in Alice, and you see, woohoo, there's the data here. We're then going to create the Genesis block, right? So we have a bunch of named coins, and this may be very different than anything else you've seen. This is just a lightweight prototype. It's not the actual implementation detail. It's just easier to explain. So we have Gen A starting at this public key. It's not actually signed. That's because the Genesis block is well published. Everybody's agreed to it. It's embedded into the code, blah, 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 blah. But when we want to actually perform the first transaction, well, we wind it. Yes, yes. Come on. There we go. Oh, wait. So what we're going to do is, since Alice owns the A key, she's going to sign it over to Bob's public key. And we do that by calling c.sign. And we're going to push that into the signature chain of C. We then want to verify that the owner at the first array index has been signed off by the previous owner. So hit enter. You'll see that Gen A is now 2 items. The first item is just the public key. The second item, you know, like, what is that? What is that? Well, I wind up just saying c.verify like I did it above, gen.a1, right, which is the one with the data, and then gen.a0. So think of it as a linked list. You're checking that the second item in the list has been signed off by the private key in the first one. So when I run that, I do indeed get Bob's public key back. So we have a cryptographic signature that Alice has handed the coin over to Bob. Now we have Bob, and Bob wants to transmit some data. So let's jump down to, so owner is the proof of that. We're going to jump to right, whoops. So now Bob wants to relay data through Carl. So, okay, so that line there is Alice handing it over to Bob. So we now have the new owner, gen.a, which is that particular coin. We're going to push that Bob is signing the coin over to Carl's public key. And then we want to verify, again, same thing as we did before, that the owner at gen.a2, if you wind up doing c.verify, gen.a2 is indeed relative to the owner, and owner is Bob's public key, right? So pretty simple, pretty straightforward signature chain. Yeah?
So from an application standpoint, how does Carl get involved? So I'm a sender of a message. I know who I want to send a message to. How does Carl implement this?
Like public key distribution?
Okay, so there's like a server where
I would not recommend using a server for distributing public keys. I'm glad you asked this. So this one of the reasons why Marty has joined our team, who is the very first contributor to Bitcoin after Satoshi, has had the most interaction with Satoshi of all people on the planet. Marty has already solved this. In fact, he solved it 3 years ago, but nobody noticed or cared. So he has a system that allows us to do public. It's kind of like PGP on steroids or Keybase, but fully decentralized and fully peer-to-peer. So I'd love to answer that in more detail, but we had Marty out to talk about it a few months ago. We can pull him out again. Can I kind of postpone that for maybe a talk that Marty could do? Okay. So yeah, public key distribution is the weakest link in all cryptographic systems, so be careful about that. Thank you for pointing it out as a public announcement. Oh wait, let me jump back to the.
before key distribution, I was wondering about routing. Like, so essentially, we're trying to send a message.
Yes.
How do I know the route?
Correct.
It's like sign you the key, right? That's all this is.
So
how do I figure out the route?
I do have a solution. However, my colleagues at MIT said that there's so much existing history. They quoted me like 10 different papers on decentralized incentivized routing that I have decided to kind of be fuzzy about that subject because one of the existing papers might have a better implementation than what we've come up with. So the quick summary, and this isn't going to satisfy you, is that the AX mining servers are technically operating under a federated structure, but allowing peer-to-peer underneath. So it doesn't violate the peer-to-peer network. These federated super peers, as I like to call them rather than servers, these propagating peers have a radix DHT where they shard the public keys of the connected users across their DHT. And because a radix tree has effectively 0.1 lookup speed relative to total data set size, O in terms of depth size of the radix tree, but that's, it's nothing compared to the total data set size. We're able to do a very efficient, neighbor DHT algorithm that then gets to Bob's computer connected to a certain peer. And then once Bob receives that, he's able to temporarily connect to the server that Alice was radix sharded to, or a common middleman server if that server can't handle it. Is that satisfying for a quick answer?
Yeah.
Are you familiar with like radix data structures and doing that from a DHT side?
Not really, but I'm familiar
Okay.
with DHT, right? Which kind of makes sense.
Yeah. All right. So a DHT actually is probably pretty terrible performance compared to a radix DHT. So woohoo! All right. So the last thing now is the mining. How's it? It's 8:30 already.
Jesus.
I'm.
You're out of time.
I have a ton of other materials. Should I be skipping this or?
We'll give you 15 more minutes.
Okay. Cool. So now we're going to get down to this point where, okay, if Carl has if Bob assigned the coin over to Carl, well, let me get rid of that. Okay. So gen.a is now 560 bytes. We're almost approaching half kilobyte. So that just in 3 transactions, the byte size, bandwidth side is just exploding. As you would expect in cryptographic systems, we don't have a trusted middleman. Yay, because I'd much rather have the waste than a middleman. What Carl's able to do, because now he owns the coin, he's going to perform C.work, which is PBKDF2 underneath, could be SHA-256, whatever you want. I use PBKDF2 for the work function on the login system, which I may not have time to cover. And Carl then adds this new mined coin to a block. It doesn't necessarily have to be a block. It could just be, he could just sync the coin to other peers. And now you'll see that this block has A through H in this new coin here. And the value on that is Carl's public key. Every other peer is able to verify that this is true because they can take, because they might not know if this is a fraudulent coin or not, a counterfeit coin. They can also take the Genesis A coin up to just the A token up to that point that Bob did the Merkle hash on it, and put in the public key that is claiming to correspond to that, and they will produce the exact same mined thing as before. Like pretty straightforward cryptographic verification. Like this is just simple, obvious stuff that you can even do in the browser, even though nobody else or very few people are actually capable of doing it in the browser. We've already built that all out for you guys. So the difference here is pretty, only on 3 signatures. It's still pretty large. The new coin is 64 bytes. The previous signature chain was 509. So you can see, you probably don't want to mine the coin every 3 signature chains, but this is how you achieve scalability in a high throughput, low latency system. It does take time for a coin to be circulated, so there's a constant trade-off between performance and work and stuff like that. But that's, could be a more detailed conversation.
And if the message takes 2 different routes, who gets the coin? And gets delivered successfully?
Yeah, so when I mentioned that you might contact multiple peers and choose multiple peers, you're paying separate coins for both of them. So there is no one coin for one route. You're sending any data over WebRTC, WebSockets, UDP, TCP, whatever it is, UDP to a server, that server is expecting to have a token and then increase it. Does that make sense? All right, so what is C? What is this thing that I was showing you that's running the browser? It's more acronyms. All right, so this is the stack. So we have ham underneath, then gun, then C, then rad, dam, axe, arrow, all the way up to the top. So we've had to build out an entire stack of stuff. You can think of it as being equivalent to this, right? There is a conflict resolution algorithm underneath the CRDT, which hopefully I'll actually now be able to start talking about. The data structure, which is gun, the security to authorization layer, the serialization to storage layer, the networking layer, which is DAM, and then AX, which I was just explaining to you guys. There's actually, there's a lot of questions to answer because I only showed you kind of the tip of the iceberg, and there's all this tech that we've built out over the last 40 years underneath. And by 4 years, I mean Feroz of WebTorrent, Juan of IPFS Filecoin, Matthias and Dat, Substack, who's pretty popular in the Node community, all huddled together in 2014 to talk about our different approaches to solving these decentralized problems. And we've all gone our own different ways, you know, Secure Scuttlebutt, DAT, IPFS, and Gun, but like this has been some pretty early work from a long time. It's not this new thing that we've just shown up in the last year and throwing things together. I did move into the Bay Area in August, so that's pretty recent, but elsewise, it's been around for a while. So HAM is our specific CRDT, conflict-free replicated data type. It's called hypothetical amnesia machine. I'll leave the naming as a separate thing we can talk about. Finally, we get to CRDTs, and why CRDTs are going to be better than blockchains, DAGs, and append-only logs, and hash-based structures. So aka all of the decentralized competitors. So let's jump back into code base and hit refresh, clear out. And I'm going to show you, I've never explained our CRDT this way before, but I'm going to show it through code. I actually hate switch statements. So this does not represent my code base. A mathematician at Stanford that I was working with said that, oh, if you want to formalize it, give me a switch statement version, and then we can convert it into latex and stuff like that. So I did. But we have a whole cartoon explainer on how the CRDT works if you want to learn about how it works from like I'm 5 side of the equation. In this specific setting, we're going to go over several different tests. So there's going to be data that Alice has. There's going to be data that Bob has. And we're going to print out what that data is before it runs through the convergent function, the commutative replicated data type, the CRDT. And for the sake of demonstration, I'm just mutating the data. And we should expect that Alice and Bob, after it's gone through HAM, converge to the exact same data. And the cool thing is, this is run in opposite orders. So Alice, Bob, Bob, Alice. And it also means it can be run independently, concurrently, on separate machines and get deterministic resolution. So we don't, I'll let brag about how cool that is because we don't have to go through a consensus system. We get determinism for free. So the first one is we have data A, state 1, data B, state 2. It runs through the system, and both Alice and Bob are now at data B, state 2 for that edge case. Now we're going to test every possible edge case of this system. Next setup is you have data A, state 5, data B, state 2. So you notice that the states kind of changed order here, and the data was the same. We run through it, and both Alice and Bob converge to the idempotent operation of the other person without having to communicate to each other about the operation. They have to transmit the data, but it doesn't matter the order that they apply it in. And they magically show up at, well, magic, it's just like, I don't know, 40 lines of switch statements. Ugh. So it's not too complicated. So the next one is, so A2, what if there's no difference between the data? They run it through, and yeah, nothing changes. It converges. So then the next one is you have data A, state 2, and then data B, state 2. So now it's the states are the same, the vectors are the same, but the data is different. So most systems out here fail at this test. So if you were to naively apply timestamps, or if you were to naively apply a lot of Lampour's work with vector clocks, is they kind of get around conflict, but when the states actually have the exact same matching numbers, it doesn't know what to do. And in our case, it actually does know what to do. We do converge to data B, state 2, data B, state 2. So that's, it seems like on, let me double check, on state 2, yes, on this one. They both converge. I know that sounds so trivial, but like for whatever reason, 100 years of computer science, nobody bothered to actually solve that problem. Next edge case is states are the same, but we have reversed the order on the data. So they both converge to B state true. This is probably getting boring at this point. We run through another edge case, B and A versus state 2, and then it both converge independently to the same data structure. And what if we have an attacker? So we have Alice and Bob and Carl. Carl is at state 9, And 9 is actually larger than a vector that, significantly larger than the vectors that the other machines are already at. It doesn't matter. If Carl, so this is effectively the timestamp attack, where if I set my local clock to 2 years in the future and using timestamp to resolve data, then the largest timestamp is always going to win, which is terrible because then people just keep on putting their clocks higher and higher and higher. This system is not vulnerable to that attack. You see that Alice and Bob do wind up staying at their converged state, and Carl is kind of left as a pitiful, terrible, attacker that doesn't win anything. All right, so for sake of time, obviously there's a ton of questions on that. I've spent 45 minutes in a talk out in Berlin with Kyle Kingsbury and the Redis author and a couple other people. Kyle Kingsbury is Jepson Test explaining the system, so that would be a whole long talk itself, trying to squeeze it in, and I'm already way over time. So CRDTs, way cool. I want you to walk away with this mind-blowing realization that might not be, it looks so simple, but this gives us deterministic, eventually consistent systems with no extra coordination, with no POW or POS or any other fancy algorithm that people might come up with. So you're.
CRDTs in blockchains these days?
Are people using CRDTs?
Yeah.
There's a ton of people that are moving to it now that CRDT is a new buzzword. I've been working on this for, what?
What does it stand for?
There's a couple different, the main definition is conflict-free replicated data types. Obviously, that conflict-free, the F is not there. So other variations is commutative replicated data type, which as a mathematician I prefer because the operations are commutative. It doesn't matter what order you apply them, they result in the same thing. You might also see convergent replicated data types. So, but conflict-free replicated data type, we'll pull them up.
Don't they get confused with DAGs?
Yeah, so this is where, yes. So give me 2 seconds. So once we have a conflict resolution algorithm that can sync data and gives us high performance deterministic consensus, I don't even want to call it consensus because it's just purely deterministic. We just have to apply that to a data structure. So we have to create a data structure that can be fed into that. And that's what Gun is, Graph Universe Node. It's a graph database. And because graphs represent any data structure, a table, or a column store is just a matrix in math, and a matrix in math can be represented as a graph. A document or NoSQL database, a document is just a tree in math, and a tree in math can be represented as a graph. But not all graphs can be represented purely as a table or as a document. What that means is a graph is a superstructure from a data structure standpoint. And if graphs can represent all other data structures, and we have a conflict resolution algorithm for it, we're actually able to generalize all data. Now, there might be some edge cases for your business application you have to modify, but the point being is that should be very mind-boggling and shattering because you have a very simple algorithm with a very simple data structure that is generalizable to effectively everything. All right, so why did I build a graph database? Well, in 1960s, the navigational databases, they're actually kind of like graph databases. They're really awesome. But nobody liked them in favor of doing it the hard way with SQL. And in the 1980s, they actually tried to create dedicated hardware. So not actual ASICs, but dedicated hardware for SQL. It was a total flop. Just wound up being that you could do B-tree indexes on SQL to get a lot more performance advantages than having hardware. So then we evolved into, we love our relational data, but all of the managers want to have the relational data spit out as a report. So we're going to have to have an object relational mapping such that we can get the object, which is the aggregated view of the data, and show that object as effectively a report to our people. So everybody got on the Java bandwagon craze of objects, and somebody clever in 2000 was like, hey, why don't we just have a database as a document in the first place? Well, we regretted that. And blockchain didn't actually come as a solution to that problem, but you can think of a blockchain as a document that's being modified by many different people and then cryptographically snapshotted at each point. So I don't think it's coincidence that a blockchain is solving the consistency issues of a document structure, but guaranteeing it like you would expect from a relational database. I predict that the future, and I'm biased, is not in directed acyclic graphs. It's just in flat-out graphs. And the reason why is because directed acyclic graphs are still effectively an append-only structure. So think of all the code that you write, and you're using Git probably for most of it, or for smarter people, Mercurial. If the Rust implementation of Mercurial, for the really smart people, I still use Git. I'm one of those poor, pathetic people. I don't like Git, but Git has to store the entire history. You wind up trying to rebase, but you have to make sure that all other peers agree with the rebase, blah, 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 blah. A directed acyclic graph is just another way to say an append-only log, and append-only logs do not scale at the end of the day when you're doing hundreds of terabytes of traffic of kitten photos and random YouTube videos that people are watching. Because if we're keeping hundreds of terabytes of traffic every single second thrown into some blockchain over all of time, no, at some point you need to clean up. You need to get rid of that garbage. You need to let the person's Facebook profile that they can drag and drop and put in a new profile photo and that mutate the previous data. The consumers want that type of experience. Sure, you can also store the history if you want, but the peer-to-peer algorithms should not depend upon the limitations of an immutable append. And this is very controversial because everybody's been on an immutable craze. But if you are able to do, and that's largely because the only way to solve a lot of peer-to-peer problems is by throwing immutable at it. So immutable became popular because it allowed for a lot of decentralized tech to exist. But that's not scalable, and it's part of the reason why I've hit these problems. So if you're able to come up with a peer-to-peer algorithm that allows for immutable data, you've in one fell swoop solved so many of these issues. So not DAGs. DAGs are great, but they still have the fundamental problem underneath them. It's just graphs, just mutable graphs. OK, but what is that C thing? So C is an almost blockchain. That's what I was showing up here. But I wanted to show what was underneath stuff from before. If you have a mutable data structure, how do you cryptographically verify all this? So C is a almost blockchain because we can have a cryptographically linked graph that is owned by a user, that is owned by a public key pair. Okay? So that means the person who owns this user graph is able to mutate anything in that graph, but it's still cryptographically secure. It can still be verified fully peer-to-peer and decentralized. Does that make sense? So you get the best components of the cryptography side with users being able to modify their data, and then it's fairly trivial to just intertwine several different users' data to produce the results that you want. And more importantly on that component is if the users are able to mutate that, you're able to get all the efficiency advantages on top. Of course, you can also have an audit log if you want, but like that solves so many of the problems. And then a call out to Marty, again, who's working on decentralized identity. One of the most dangerous problems of this approach is Axe doesn't have this problem, but just this problem right here of decentralized cryptographically secure user graphs is you could have a Sybil attack, right? You could have somebody that creates 1 million cryptographically secure user accounts and tries to use that to spam systems. Marty, with his identity system, has been able to confirm the research by scientists on the Kevin Bacon effect, that supposedly within 6 or 5 degrees of separation, you're connected to everybody in the world. He ran his identify system across, he mined a bunch of Bitcoin miner data and Bitcoin wallets. And he ran this with Identify, his peer-to-peer identity system. And he wound up seeing that there was a sharp fall off after 5 degrees of connectivity, of peer-to-peer relationships, that after 5 degrees, he could isolate like thousands and thousands of public keys that were effectively a botnet. You'll have to come back and talk at some point. So even that problem at this layer is solved. All right, ugly clothes reminder, I'm going to have to skip this for timing's sake. It's already over time from the 15 minutes. I was just going to show you how the user login system, I can explain it really quickly. 2 minutes? I mean, I can probably do it in 2 minutes. Oops. Again, cryptography is easy. It's just a lot of people in the blockchain world that have made it hard by trying to run decentralized networks to simulate centralized behavior. You're fighting physics at that point. You're creating systems that are fundamentally not scalable. What are people thinking? All right, so this is how it works. OK. Let me scroll up. So I'm not going to go line by line, but all right, we generate our key pair. We then have an alias of Alice, so that's your username. You have a passphrase, hopefully better than secret. That should be banned. You have assault, whatever your nonce you want should be safer than that. You then take the PBKDF2 extension of the combination of the alias and the salt. You could do it with the pass phrase. I don't recommend that, or at least the internet didn't recommend that. But so use the nonce, use the salt instead, because it's more secure. The point being is you could theoretically do this. You create a proof of work, PBKDF2 extension, if you're familiar with that cryptographic algorithm. You then take the proof that's a result of that work and encrypt your key pair with that proof with a symmetric algorithm like AES. And in our case, we're using AES-256. Specifically, I want to say don't do this with your Bitcoin wallet, but for pretty much all social media content, pretty good. And then Marty system is able to deal with hijacks and stuff like that. So now it prints out the public key as before up there, which is the first console.log. The second one is the encrypted version of your keys. And then we're going to attempt to log in. We take the username and passphrase. We create more work, so this prevents brute force attacks by attackers. We then use that login, which is the proof of work, as the AES decryption key to pull your keys back out. And now you've logged back in. So ladies and gentlemen, you don't leave it to Civic or some blockchain system or Ethereum to have these username systems. Like literally in just 7 lines of simple cryptography, you've solved multi-user, multi-device, cryptographically secure login. And if I were to show you the rest of the demo, except for the batteries dying here, we're even able to do password resets with this mechanism without a server. So I forget what my password was. That doesn't help. Oh, OK, so it's safe. So I just changed my password there. And that's because the passphrase and alias, you do not derive the keys from your passphrase. You just associate the passphrase with it. And then we have also a password reset mechanism. It's not too good. There's actually some better ones out there, but it was simple to implement. All right, so that was hopefully less than 2 minutes. Oh, that was 3 minutes. And
1 minute.
So that if you were curious, the demo I showed at the beginning, no, there's no hand waving I'm doing with having a central server. You can actually have regular user-based logins, yet be fully peer-to-peer and cryptographically secure. Yes. Oh wait.
What was the key derived from, sorry? Where was the randomness derived?
The key is technically just a flat-out ECDSA key. Right? In this specific case, it could be RSA or whatever else you want. So it's just independently generated. So it's actually cryptographically safe. There's other people who are producing private keys based off of like passphrases, and that's ridiculous because then the user can't even. Correct. Yes. Yes. So that problem does not exist with our system. Oh wait. Ugly slide. RAD. It's just our storage engine, and we're still working on it. Daisy chain ad hoc mesh networking. This is from a networking layer. And again, I'm not going to go over the algorithm of RAD. I'm not going to go over the algorithm of DAM because that's a separate discussion. What?
Which of these projects are you working on?
Yes. Let me go up to this. So we've built from here all the way up to about here, halfway into Axe.
Which one is getting the most?
Gun, because it's so fundamental. Yeah. Well, actually, I should say I'm maintaining Gun the most. However, the most bugs exist in DAM and RAD that in C and RAD that we're fixing and tweaking. Yes, we are hiring, and we'd love people to help offload all this awesome cryptography stuff. So if you feel, engineers, people who are really good with storage engines right now, and then also people who are really good with having creative applications of cryptography. So applied cryptographers, not blockchain sure helps, but I don't want you to come into the office and be like, oh, we should solve this through POW or POS, because I'll just be like, POW, no, like, you know, the comic strip POW. I'm not abusive. I'm not abusive. Oh wait, Daisy, I mean, you can ask the other employees to verify. Yes. So I'm not really going to cover that stuff. It's just the peer-to-peer protocol underneath. And then, as you saw, the Axe. I was going to do another quick demo in 50 lines of code. You could build a very simple peer-to-peer Twitter. We're going to skip that. Again, I want to come back to this point that these pipe dreams of dApps can be done today. Not tomorrow, not later. So when to launch, it'd be really great, since we're at that layer, to have engineers that come in and help out. One of the biggest problems is making sure that we have enough of these stupid WebRTC workarounds, aka servers, that we can relay data through. So if you could help us launch some Axe peers yourself, or you could be very early on in the network, and contribute to providing free bandwidth to people that then later hopefully pays off.
Hey. Woo!